Vectors in geometric proofs. So we can use vectors when proving things geometrically, and the best way to do this is with a few examples. So let's go ahead and draw a circle, and let's draw an XY axis going through the center of the circle. And what we want to prove here is that if we take 2 points on a diameter and connect them to the circumference of the circle, so these 2 points here, and connect them to any point on the circumference of the circle, the same point, that they'll always make a 90-degree angle. So we're going to go ahead and do this with vectors. So let's go ahead and make these two lines vectors that are meeting the same place. And it's always nice when you have vectors that are coming from the origin. So let's go and add some more vectors in. So let's add in a vector going from the origin to that same point. Let's call this point B, O, A, and C. Now, if the circle has a radius of R, this would make this point A over here as R0 with its column matrix. B we don't know, so let's call it AB. And C is minus R0. And if we're going to prove that this is if AB is perpendicular to AC, one way we can do that with vectors is if their dot product is 0. So if we can prove that A to B dot product with C to B is equal to 0, we will successfully prove that AB and CB are perpendicular. So this is what we're required to prove. So in order to do that, we need to get expressions for our vectors AB and CB. So we can get the vector AB by just subtracting our components B and A. So we can say that A to B is going to equal A minus R, I, plus B minus 0, J. And you can do the same thing for CB. So it's important in the order of this. So for CB, we're taking the components of B. So it's going to be A minus R, I, and we're going to have plus B minus 0, J. So our vector AB is just going to be A minus RI plus BJ. Then we're going to have A plus R I plus BJ. And now we can go ahead and find the dot product of these two vectors. So the dot product of AB and CB is just going to be its x components multiplied together, so A minus R times A plus R, plus its B components multiplied together, so it's just going to be B times B. We expand these brackets, so we're going to get A squared plus AR minus AR minus R squared plus B squared. The AR and the AR will cancel out, so we get A squared plus B squared minus R squared. So we're close. If we can see from our circle, this also has a distance of R, the vector OB, and its x component is A and its y component is B. So just using some simple Pythagoras, we know that r squared equals a squared plus b squared. So we can go ahead and substitute in a squared plus b squared is equal to r squared. So we get r squared minus r squared, which is 0. And we've successfully proved that the dot product is 0, which means that it doesn't matter where this point B is, the dot product will always be 0 and the lines will always be perpendicular. Let's have a look at another example. We're going to draw up a rhombus. And we want to prove that the diagonals of a rhombus always bisect the angles at the vertex, which means that we always want this angle to equal this angle. And we're going to do this with vectors. So to do that, let's draw in some vectors. Let's make all these lines vectors. So I like the vectors to be parallel, the ones in the same direction. So let's go this one, and let's go ahead and make that point that way. You can pretty much point these any way you want, but try and be consistent. Ones that are parallel, make them point the same way just for ease. So if we call this vector A, this will be vector A. And if this is vector B, this will be vector B. I was careful not to use A for this vector because it's not pointing in the same direction as this vector. So even though they're going to have the same magnitude because it's a rhombus, I can't call this vector A because it's not pointing in the same direction as this one, but this one is. So I can call this one vector A, and you can see that going from A then to B is the same thing as here. So that's clearly the vector A plus B. And if we're going to prove that the diagonal in a rhombus always bisects the angle at the vertex, that just means that the dot product of this vector and this vector always has to be the same as the dot product of this vector and this vector. So that's essentially, if we can show that, we can prove that the diagonal always bisects the angle. So we need to show that, so we're required to prove that B dot with A plus B is going to be the same as A dot A plus B. So they're going to have to be the same if we can show that. So, because it's a rhombus, let's just note down some things. We know that the magnitude of A actually is definitely going to equal the magnitude of B. And that also implies that the magnitude of A squared will also be the same as the magnitude of B squared. Okay, so let's take the left-hand side and dot product this out. We're just going to get dot product of B and A. You can write it as A dot B, and then times B and B, which is going to be B dot B. So we're going to get A dot B plus, then we have our special result where we multiply dot product two of the same vectors together. It's the same thing as the magnitude squared of that vector. And then we also have the property, because this is a rhombus, that the magnitude of B squared is the same thing as A squared. So let's take our right hand side and multiply it out. So we're going to have A times A, which is just A dot A, plus A times B will just be A dot B. A times A, special result again, which is just going to be the magnitude of A squared plus A dot B, and that equals the left-hand side. So we've successfully shown that the dot product of this will always be true. And that means that the diagonal always bisects the angle at the vertex in a rhombus.